Okay, welcome everybody. It's me again. This time not as a PyGrace organizer, but as a Python core developer. And I'm gonna be talking about uncovering the magic of implementing a Python syntax feature. Um, so a little bit about me. Apart from doing all of the a lot of the organizing here at PyCon Greece, my full-time job is at Quantsite Labs, where I get to spend most of my time working on Python and a lot of stuff in the Python ecosystem. I've worked quite a bit on NumPy as well lately, but a lot of my time goes towards Python core, which is what I'm going to be talking about today. Python 3.14 is the new exciting version of Python. um, Hugo is here, and he's the release manager for Python 3.14. It's also the Py version of Python, so it's something to be really excited about. It comes with a lot of great stuff, and we've worked a lot of volunteer hours gone into the new version of Python, a lot of new features as well, but I'm going to be talking about a specific one today. I'm I'm going to be talking about PEP 750 template strings. This is something that was in the making for years. It's just that we couldn't settle on one specific thing, but then after lots and lots and lots of discussions, we actually did settle on one thing. We found the right thing. PEP 750 got accepted, and then I was the one that working on its implementation, though I didn't really I was somewhat involved in the specification as well, but not a lot. I mainly did the implementation. Um, so T strings, what's a T string? It sort of feels like an F string, um, but without the F prefix, with a T prefix. And what it allows you to do is do something like that. So T strings are not really strings internally. They give out a new type, which is called template, and it allows you to basically sort of um, uh, get into the interpolated stuff inside the T string. So for this example is not really interesting. It's sort of the hello world. But if you have something like this, so you have an actual interpolated value, in this case called Athens, then it's not like with the F strings where you don't get no control over how it's interpolated inside the final string. In T strings, you actually get an object that gives you access to that underlying value of the thing you're interpolating, of the variable you're using, and then you can do all sort of nasty stuff with that. And it's actually a really interesting thing because you can do crazy stuff like for example, write a utility that's called capitalize. And what capitalize does is takes the values, the things you're interpolating inside the curly braces, and capitalizes those words. So for example, in this specific utility, uh, any string we have, so all of the things that are not interpolated, that are actually string literals, we're using as they are, but any interpolations we actually call title on, so they're going to be capitalized. And so when we actually get this, we can use the T string, we can call capitalize on it, and then Athens will actually be capitalized. So we get access to the values of the variable we're interpolating with, and that gives us power to do whatever we want in terms of transformations before that value gets added to the final string. This gives us power to do stuff like we could think something like an HTML with T-strings, where it sort of works like React would work, or it gives us the power to do stuff like structured logging, where log and a T-string would actually be like maybe a JSON for some use cases for a log collector, or a string in some other cases for human readable stuff. So it's a really powerful thing. But we're not actually here to talk about T strings themselves. There's going to be other talks you can attend on that. We're actually here to talk about implementation and how T strings are implemented and how syntax features are implemented in Python. A note before we go on is that there's not one Python, there's a lot of Pythons. And the one we're working on is CPython. That's the reference implementation and the one that came up first. But there's a lot of other Pythons. There's Jython implemented in Java for the JVM. There's PyPy, which is Python implemented in Python. There is IronPython, which is the Python implementation for the .NET platform. So there's a lot of Pythons. What we're going to be talking about today is actually specific to CPython, the reference implementation, the one implemented in C. So, what's syntax? We're going to talk about syntax features. Not all features are syntax features. Some of them are. Which ones? We have many examples. For example, T-strings is a syntax feature because it adds a new syntax to the language. That T prefix is a new syntactic construct you can use. Type parameters and the type keyword, new syntax, new keywords, that's also a syntax feature. Except star, which is something that was added in 3.12, I want to say, but I'm not sure. Except star is also a new syntax feature because it adds new syntax. The match statement, structured pattern matching, is a syntax feature. And parenthesized context managers, not such a huge feature, but still very helpful. That's a syntax feature as well. Not everything is a syntax feature. In 3.13, we have a lot of new stuff. We have free threading, which is basically making Python thread safe and making it possible to run Python without the GIL. We have a JIT, which is a just-in-time compiler. And we have the per interpreter GIL is sort of the in the same parallel as free threading, but sort of using another mechanism to allow parallelism. That's also not a syntax feature. So now that we know what syntax is, we can talk about how syntax is implemented in Python. The syntax implementation is comprised of 4 steps. The first is the tokenizer, the second is the parser, the third is the bytecode compiler, and then the fourth and final step is taking what the 3 first have done and interpreting that in order to run Python programs. So the tokenizer, the input is the source code you're writing, and the output is a stream of tokens that can be interpreted by later stages of the compiler. What the tokenizer does is breaks down the characters. There you go. Breaks down the characters, the source code, into meaningful parts. So stuff like white space gets ignored, stuff like comments get ignored. It's just the stuff the compiler actually needs in a format that the compiler can understand easily. How does a tokenizer work? So it's a very, very complicated piece, the CPython tokenizer, but in essence, all it does is keeps track of where it is, and then reads the new character and tries to append that to a token. So, for example, here we have 2 pointers: the start of the token and the current character, and the current character actually goes forward, and then where are we? Yes, there you go. Goes forward, and then the tokenizer actually sees that there's a new token that's called t-string start. And then the same story happens, and the tokenizer knows about how each token is formed. So, for example, it knows that T followed by a quotation mark, any quotation mark, is a T-string start token. So it does that play where it reads in the new character, asks itself, is this a token? And if not, it goes on and on and on. So, for example, the next token is going to be hello, and that's a T-string middle. uh, here you go. That's a T-string middle. And then the brace is a token by itself. Then the value is going to be a name token. And the tokenizer actually knows about all of these stuff. And then the brace is a token by itself, and then the final quotation mark is a token we call T-string AND. And so the source code has now been broken into pieces the compiler can understand in order to do what you want it to do. So this stream of tokens can now be used from the subsequent steps of the compiler to get to the final stages of running your program. Writing code to correctly recognize the new tokens is what we need to do every time we need to add a new syntactic features, and it's really easier said than done because the tokenizer is so huge nowadays. It's really complicated. It's all handwritten, nothing generated. So it's most of the times it's really complicated to work on the tokenizer. So yeah, that's what one needs to do in order to work on the tokenizer. The next step in all of this is the parser. What the parser does is it basically analyzes the tokens we broke down the source code into before, and then constructs a tree-like structure that the compiler can take and understand later on. So we went from source code to tokens, and then from tokens, we're now going to a syntactic tree. We call that the AST, the abstract syntax tree. And the way the parser works is by using a grammar. So what the grammar does is it defines the syntax of the language. It defines. So, for example, after a T-string start, we need to absolutely see a T-string end at some point. If that's not the case, then we have a syntax error. So the grammar is responsible for doing all of that. And the way the parser works is it takes every token and checks whether the stream of tokens that we have is actually defined in terms of the grammar we have. So in this case, T-string start is matched, so the parser is happy. Then it goes on to the next thing. When we have lowercase letters, that's other rules. So the grammar is comprised from lots and lots of rules that the grammar uses to actually represent that syntax. The next step is that's another rule. So in this case, the brace is not matched. That's because in this case we do not have a brace in the next token. We have something else. We have a T-string middle. So every time something fails, we go back up, we backtrack, we go to the previous rule and try the next alternative. The vertical bars actually separate alternatives, and when one fails, we go and try the next one. So for example, here we say if it's not a brace, then it needs to be a T-string middle. In this case, it actually is a T-string middle, so the parser keeps on being happy and accepts the input that it has. This dance goes on and on and on. We then have a brace. Annotated right-hand side is another rule. You're going to have to trust me that the name actually matches. And then there's also optional stuff. And in case we don't match those optional stuff, we're still happy. So we don't need to backtrack. We can just keep on. And at the end, we match the brace as well. And then there's the dance of trying to find whether we match. For example, we see whether the brace matches, it does not. And then the end actually does. And the fact that everything matches and we don't have any remaining tokens means that this is valid syntax and the parser is happy, can go on to the next step. I've lied a bit. The grammar does not actually look like the one that I showed. It actually looks something like that. It's a bit more complicated. And if we zoom in, You'll see a lot of stuff that's happening there. We have stuff like types in the grammar. We have stuff like flags. For example, the memo flag means that if this actually parses, then save that result. And if we come back to this rule, just use that result. It's sort of a cache. Um, there's also variables that can be used in the other stuff. The other stuff is the thing between the braces. It's called the grammar action. And if you remember before, I'd mentioned that um, that the parser not only verifies that the syntax is okay, it actually constructs a tree-like thing as well. And what the grammar action does is it incorporates C code inside the grammar that actually constructs that tree. That grammar uh, that we showed before is actually going to generate this following tree. We start with a template string. This is all AST nodes that get constructed from the grammar we showed. So from the tokens, we go to the tree that looks like this. The template string has a couple of values. The first value is a constant because we have the value hello before we actually interpolate stuff. And then we have an interpolation that's comprised from a value which is a name, and that name has the ID value. The interpolation has some more meta information in it. You can see that we have a name with the ID value and then the constant value. That's because we save both the name of the thing, and we also save what actually is between the braces in interpolated values. And that's because we need it later on for stuff in the compiler phase. Oh, actually in the interpretation phase. So the way to work on the parser, and that's where most of my specialty is to write grammar rules. And that's actually really easy because you don't need to write any code at all. You can just write grammar rules that verify that the grammar is correctly checked. And then you only need to write an action that will construct the AST. And that's actually easy. It's really easy because we have written a code generator that takes that grammar and produces C code that does all of the processing. Another thing that you might have seen and be wondering about before is what are those invalid rules? Apart from the rules that will match correct syntax, we also have rules that will match invalid syntax, and that's we use those to do a smart thing, and that smart thing is raise syntax errors that have helpful messages. So in cases like this, for example, if we have just an equal sign between the braces, the grammar will actually match that and say, oh, I know what this looks like, and I know what the error message should be for this. And in this case, it's valid expression required before the equal sign. So in the grammar, we're not only matching valid syntax, we're matching some invalid syntax as well. That's going to produce a helpful syntax error so that users know what they've done wrong. Um, the third step in this compiler dance is the bytecode compiler. The bytecode compiler takes the abstract syntax tree, the syntax tree we talked about before, and produces bytecode. And you can think of bytecode like as machine code, but not for the CPU, but for the Python CPU. We call it the virtual machine. So bytecode is basically elemental instructions to the Python virtual machine on how to do things. And the bytecode compiler takes the syntax tree, produces that bytecode so that Python can then run your programs. It compiles down to bytecode. That's why it's called a compiler. So we have that tree we constructed before in the parser phase, and we go down that tree, and all we need to do is take each node of the tree and produce a bytecode instruction out of it. So for example, the bytecode compiler knows that the template string comprises of a constant, and whenever we see a constant, we actually think load const. And load const is a bytecode that says take a constant and load it into the virtual machine. Then what's the constant? The constant is hello. We go to the next one. We have an interpolation. Before we go into the interpolation, we actually go back up to the template string. And then it knows that it's all done with a constant. It builds a tuple. This is all basically implementation details of how T-strings are implemented. That's why I'm not going into very much detail into why the load const empty string is there and why the build tuple is there. But when it sees the interpolation, it's actually a bit easier. It loads the name because it sees a name node. It knows what the ID is, so it adds it as a parameter. It loads a constant again. And then the interpolation is a build interpolation instruction with the argument 2, just because there's 2 elements in it. So that's it. Then we build another tuple. You're gonna figure it out why all those instructions are there a bit later on, but you have to trust me that they're there for a good reason. At the end, we have a build tuple. A build template, I mean, and that's what actually builds the final template type. So this is the bytecode that a T-string actually produces, and this is what will later on get run in order to for Python to run your program. There's a question here, and it is, can we do any optimizations on this piece of bytecode? And the answer is yes, otherwise it wouldn't be on a slide. Can anyone see what sort of optimizations we can do here? It's not very, very hard, but if you see the first 3 instructions, you'll understand that we do 2 load constants, and then we build a tuple, which means that instead of doing 2 load constants, we can do 1 load constant. So the 3 first instructions will actually become, it's this way, will actually become load constant the tuple. So instead of doing load constant a string and another string and then build a tuple, we just load the constant 2-element tuple a string and empty string. So we have 2 bytecodes less to execute at the end. There's a lot of other optimizations that are happening, but that's for someone else to talk about because I'm not too familiar with all of them, and that's not my specialty. So at the end, what we need to do is take that those bytecode and actually run them, and that's what happens after everything is said and done. So in order to work on the bytecode compiler, we have to write actual compilation code. It's not generated like we said about the parser. It's writing the actual code that sort of walks the tree and then takes each node and produces the associated bytecode. It's not as challenging as a tokenizer, but it's still challenging because it's not generated, and anytime you have to write code about something like that, it's a little bit challenging. That's a bytecode compiler. What's the next step? The next step is the interpreter. So we're done with the compilation phase. We're done basically processing input. Now we get to the actual execution of the code. What the interpreter does is basically evaluates. So it goes through the bytecode the compiler has produced, evaluates each bytecode, and runs the program. So having this bytecode, we need to be reminded that Python is a stack-based virtual machine, which means that anytime we load something or we store something, we load it into the stack or we store it, we pop it from the stack and store it in memory. So everything that's happening inside Python is basically pushing things onto the stack there is somewhere or popping things from that stack. So for example, the first instruction is load const, which is load something onto the stack. The second instruction is a load name. What that does is goes to the symbol table, finds a variable with that name, and loads the value onto the stack. In this example, we know that the variable has the value Athens, so we load that onto the stack. Then we load another thing, the constant value. So we now have three things on the stack, and then build interpolation 2. The 2 is actually the amount of things we should pop before building the interpolation. So what happens here is we build an interpolation object with 2 values, and then we push that interpolation object onto the stack again. So every bytecode is very, very elemental. What it does is getting things from the stack, doing some transformation, building something, and then push it back onto the stack. And then we have a build tuple. Build tuple 1 means get that last thing from the stack, build a tuple around it, and push it again onto the stack. And then build template is what actually takes both of those things and produces the final template type. So now, from the beginning, we've gone full circle. And from the source code, we went to tokens, then we went to a tree, then we went to a bytecode, and then that bytecode was evaluated to give us the final template type. The bytecode working on the interpreter is not easier in any means, but the thing that makes it a tiny bit easier is that it's a domain specific language. The whole interpreter is defined in a very specific way, which means that writing a bytecode instruction doesn't actually require writing a lot of code. It's mostly writing code in that DSL, and that makes it a tiny bit easier. It's actually a fairly bit easier than it actually sounds. So yeah, to recap, the Python implementation comprises of 4 steps. We went from the source code, we go through the tokenizer to tokens, then to a tree-like structure from the parser, then to bytecode from the bytecode compiler, and then that gets evaluated to give us the final code. That was a journey through the Python virtual machine. I hope you liked it. If you have any questions, I'm here to answer them. I'll be here for the whole conference, so you can come talk to me, find me, ask me questions. If you want to talk about Python or organizing or communities or anything at all, just come talk to me. That's it.